Lab 4, Oscillations. In this lab, we are using the spring mass system in the video given to model a mass oscillating on a spring. We are interested to see whether or not the system follows the energy principle. This is the preview. We are going to use Newton's second law to predict the velocity and position of the mass. Energy principle is used to determine the change of system's energy, which is equal to delta kinetic energy plus delta U gravitational plus delta U spring. Magnitude of forces and energies are used to edit the Gross script code. And here's a visual model of the system, which is not drawn to scale. I extracted the observational data using the tracker program. The point mass was used to track the x and y position of the mass, and the data was exported into a CSV file. To find stiffness using the period of oscillation, I found the average period of 1.5195 seconds based on the y position data from tracker. Then using the equation k equals 4 pi squared m over t squared, I estimated the stiffness to be 6.87 newtons per meter. From the k calculated, I was able to estimate the L0 of the spring, which is 0.127 meters. This is my glow script code. To set the initial conditions equal to the model, I've changed the ball's position and the ball's velocity. And the ball's mass was set to 0.402 kilograms. Then I used the fundamental physics principles mentioned before to modify the equation for L, which is ball's position minus spring's position, and L hat, which is L over magnitude of L. Then stretch was found to be magnitude of L minus L0. Then I've edited the system energies to compute the kinetic energy, the gravitational potential energy, spring potential energy, and the total energy, which is the sum of all three energies. To match the calculation loop, I've modified the while loop to be t less than 9.212 seconds. Then I found F net equal to F gravitational plus F spring, which was calculated using the equations mentioned before. Using Newton's second law, we were able to update the object's velocity and object's position. This is how it looks when you run the program. The red dot is the observed data, and the blue dot is the prediction. By looking at the position versus time graph, we can see that the amplitude and periods of observation approximately matches that of the prediction. However, a possible source of error that could account for the differences in amplitude could come from when I extracted position from tracker. It was hard to find the exact center of mass, and so the position could be slightly off. For my model system, the energy principle is satisfied because the change in total energy in the graph is 0, meaning the energy is conserved. Period of oscillation from the x position data was calculated to be 1.6858 seconds, while the period of oscillation from the y position data was calculated to be 1.5195 seconds. The oscillation in the x direction is like a pendulum pathway, while the oscillation in the y direction is due to the spring force and gravitational force, which is more accurate to be used in this model. The computational model has a good prediction for the observational model, and the spring mass system follows the energy principle.